If you're looking to integrate automotive functionalities like precise control, real-time data monitoring, or vehicle diagnostics of industrial machinery, you will find CAN bus indispensable. I will pivot around CAN library in this episode. Because from now on, NECTO has CAN bus officially supported. My name is Branko and welcome to another embedded episode about NECTO. If you want to design with CAN, you need to create an application project. Without further ado, I will click on New and I will select this type of a project, application type of project. Okay, another important thing is setup. I will click on New to start creating the setup inside NECTO. Because both of my CAN transmit and CAN receive microcontrollers are ST based, I could select microC AI for ARM, GCC for ARM, or I could select Clang for ARM as my preferred toolchain. Then my development board I just showed you, then the microcontroller which will hold the code, and I'll just click on Advanced and I will replace clock logic from default one to CAN clock scheme. Okay, I will not need a display for the basic CAN demo. Programming device has been automatically selected, which is kinda neat. And I'm done. Well, from now on, you're able to develop industrial or automotive apps with NECTO and CAN bus. Here are the step-by-step instructions of how CAN bus can be utilized, with the demo code included. First thing to be done, enable CAN library inside NECTO's library manager. Now, what I want to do with this library? I want to transfer some data, right? I want to create a CAN transmitter. And I want some kind of a time delay between the transmission of data. Before transmission, I need to configure a microcontroller in a proper way for CAN transmission to take place. I need to set the frequency of communication between CAN nodes, because we need to make sure frequency of CAN is the same across all the CAN nodes. Initialization method should be called as well. And CAN open method alongside CAN configure default and CAN filter configure default methods is here to initiate all of those variables in a proper way. Okay, let's perform the short overview of what we have done so far. I inserted all the CAN methods with all the associated arguments, but I never got to define them. Let's do this right away. I will insert instances of all the properties needed for CAN to work properly. And of course, make sure microcontroller has adequate pins and transceiver logic for CAN transmission to take place. How I made sure my hardware I selected has CAN pins and CAN transceiver? Well, I used SiBRAIN. SiBRAIN card, microcontroller card which has standardized outline, is being utilized for this project. In other words, this microcontroller card is going to act as a CAN transmitter. If I jump into schematic of this microcontroller card, I'm able to see the actual pin names which are dedicated for the CAN communication. And of course, here is the CAN transceiver. If the actual connection between a microcontroller and SiBRAIN card is needed for some reason, just zoom out and focus on the CAN section of the SiBRAIN card. Just remember those numbers, 43 and 44 for a moment. Getting back to NECTO and explaining the CAN pins, but now in a software way. Because this part of code is highlighted, this tells me CAN receive and CAN transmit pin macros are present somewhere in the codebase. If you were wondering where the heck is this defined, right click on the CAN receive macro, select go to definition, and here they are. One note, I told you to remember SiBRAIN card connections 43 and 44. See, here they are. Let's go all the way up, focus on the MCU card header line, right click on it, go to definition and find this macro. And here it is, the name of the actual CAN pin. And this is how you can find CAN pins if you are not 100% sure. The last thing, data to be transferred. Okay, for this explanation demo, transmit data is going to be a simple integer variable, incremented from 0 to 255 in an infinite loop. On a receiver side of the CAN bus, this incrementation will be visually presented on LEDs, which is optically compelling. I will provide some basic configuration about the actual message, which is going to be constantly sent over the CAN bus. And if you want to make sure transmit and receive are not stuck, insert some dummy data in between. And do not worry, we will filter that out. We will filter this dummy data on the CAN receive side. Transmission of data via CAN bus is done, but we have not finished the whole demo. I will focus on receiving the data now. I will try to speed up the demo, and by clicking on the code section in the top left corner of the NECTO, then selecting package manager on the top right side and typing in CAN demo for example, I am able to find both CAN transmit and CAN receive demos. I will click on the CAN receive demo, install it, open it by cloning existing CAN setup with one slight modification. I will turn off my CAN transmit board then scan for the programmer device, which is on the second board, CAN receive board. Okay, that's it. After properly configuring the CAN receive project, I am presented with the demo, which is going to perform the double check of dummy data, which is being sent by the transmit device. And finally, this demo will display incremented values on the designated port of the microcontroller, which is being labeled as the CAN receive microcontroller. What port we are talking about? Well, I will utilize port E, for example. Okay folks, that's it. After flashing the code for the CAN receiver, this is the result. Nice, useful and simple demonstration of CAN bus, which you can build with ease. The controller area network remains a dominant force in automotive applications. NECTO could be an IDE with which you will be able to develop those projects, because CAN bus is officially supported. Well, that's it. Thanks for watching. Catch you guys with the next one.